Welcome to The Explainer. Today we are diving headfirst into one of the deepest, most mind-bending questions in all of science. We're going to take your everyday idea of reality, shatter it into a million pieces, and then, using some of the weirdest ideas in physics, we're going to piece it back together into something, well, a whole lot stranger.
So, let's just kick things off with a question that, it sounds like something you debate late at night in a dorm room. Is the moon actually there when nobody's looking at it?
Now, your gut, your common sense, everything in you screams, of course it is. What a dumb question. But what's so wild is that for the past century, physics has been screaming back, nope, not so fast. It turns out that our fundamental intuition about how the world works isn't just a little off. It's profoundly, demonstrably wrong.
Okay, so before we totally blow up that common sense reality, let's actually define what we're talking about. What is this intuitive picture of the world we all carry around in our heads?
Well, in physics, this idea has a name, local realism. And it's built on two pillars that seem, completely obvious. First, local. An event happening here can't instantly affect something happening on Mars. Information has a speed limit. And second, realism. A coffee cup on your desk has definite properties. It's ceramic, it's a certain temperature, whether you're looking at it or not. The moon is still the moon.
So, put it all together, and local realism basically says that if you see two things that are perfectly correlated, say you have two coins that always land on the same side, there has to be a physical reason for it, a common cause. They came from the same factory, they're weighted the same way, it's not some kind of spooky magic.
And that's how we all thought the universe worked. It was neat, tidy, and made sense. But then, in the early 20th century, quantum mechanics came along, and it presented a deep, profound puzzle that drove one of the greatest minds in history, Albert Einstein, absolutely crazy.
You see, Einstein hated the randomness and the apparent fuzziness of quantum theory. He famously said God does not play dice because he was convinced that underneath all that quantum weirdness, there had to be a more predictable, clockwork-like reality.
And in 1935, he and his colleagues published a paper outlining a phenomenon called entanglement. This is where you have two particles linked in this bizarre way. If you measure a property of one, like its spin, you instantly know the spin of the other, even if it's on the other side of the galaxy. To Einstein, this looked like information was traveling faster than light. He dismissed it as spooky action at a distance.
And this set up the ultimate showdown. The quantum view said, nope, the particle's spin isn't decided until the very instant you measure it. But Einstein's view said, no way! The spin was decided from the very beginning. Each particle must carry a hidden instruction manual, some hidden variables that tells it what to do when measured.
For decades, this was just something physicists argued about over coffee. It was philosophy, not science, because nobody could think of a way to actually test it. Until, that is, an Irish physicist named John Bell had a brilliant idea.
In 1964, Bell came up with a genius mathematical theorem. He figured out that if Einstein's hidden instruction manuals were real, there would be a hard limit on how correlated two entangled particles could ever be. He turned a philosophical debate into a testable, physical prediction.
Bell's math created a line in the sand. Any local realist theory, any common sense theory, including Einstein's with hidden variables, could never produce a correlation value greater than 2. That was the absolute ceiling, the unbreakable speed limit for reality as we know it.
But here's the kicker. Quantum mechanics predicted a value of about 2.83. It didn't just break the common sense limit, it smashed right through it. So suddenly we had a clear, testable experiment. All you had to do was ask the universe, is the answer less than 2 or is it 2.83?
So the stage was set. The gauntlet was thrown down. Physicists around the world set out to build experiments that could actually perform this test and get a definitive answer.
And the results started rolling in. The first major experiments in the early 80s, led by a physicist named Elaine Aspect, gave a result of around 2.7, a clear violation. And then, as the technology got better and better, culminating in what are called loophole-free tests in 2015, the verdict became undeniable.
Every single time, the experimental result was much, much higher than the classical limit of 2. Every time. The universe, it turns out, is spooky. Our common sense picture of the world, local realism, isn't just a theory. It's experimentally, factually wrong.
Okay, just let that sink in for a second. This is a massive deal. This experiment basically kills the idea that objects have properties independent of us observing them. So if our most basic intuition about the world is wrong, then what's right? What is reality?
So, with our old idea of reality in shambles, how do we rebuild? Well, a fascinating new perspective suggests that maybe reality isn't this solid thing out there. Maybe reality is a consensus, something that emerges when we all agree on what we're seeing.
Think about it like this. You see a red Ferrari. Your friend Bob sees it from the side. Charlie sees it from a window up above. None of you see the whole car. But when you all compare notes, you agree, yep, it's a red car. The objective reality of the car emerges from the consensus of all your different overlapping viewpoints.
But see, in the quantum world, reaching that consensus is really tricky. There's this rule called the monogamy of entanglement. It basically means a particle can only be perfectly, maximally entangled with one other particle at a time. It's like you can't give two different people your absolute undivided attention at once. So this creates a problem. How does the universe keep a consistent story for everyone if these connections are so exclusive?
And here is the beautiful, mind-blowing twist. That spooky action at a distance that Einstein hated so much, it's not a bug in the system. It's the most important feature. Those stronger than classical correlations are the universe's clever hack. Its compression algorithm for making sure that everyone's view of reality lines up consistently.
So let's wrap this all up. The big takeaway is this. Our comfortable classical view of the world is dead. It's been proven false in the lab. And in its place is a much stranger picture, where objectivity seems to emerge from agreement between observers. And crucially, measurement doesn't just reveal a property of a particle, it helps create it. That quantum weirdness isn't a flaw, it's the very thing holding our shared reality together.
And that leaves us with one final provocative thought to chew on. If reality is a consensus, who or what gets a vote? Is it just conscious beings like us? Does a camera get a vote? What about a rock or a single atom? Where do we draw the line between an observer and the universe being observed? It's a question that blurs the line between where we end and reality itself begins.